all hear me? Perfect. Hi, everyone. My name is Vicki. I'm really excited to be talking about Blockchain 101 today. I had the great fortune to spend the summer working on building enterprise blockchain technology at Chain, which is an awesome company based here in San Francisco. And so I'm just going to be going over, what exactly a blockchain is. I don't know if y'all are plugged into all of the news and drama around cryptocurrency right now, but hopefully this will take a step back and go over some foundations. So I want to start by telling a story. And this story is about somebody named Alice. Alice, unsurprisingly much like myself, is somebody who is just about to graduate from college. She's going to pay her rent on her first apartment and wants to put a down payment. So she wants to be able to send money to her landlord. Unfortunately, Alice doesn't always have all of her things together, and she's sending this wire transfer to her landlord right as the bank is closing. It's the weekend, and her landlord was like, "You need to get it to me by Sunday." But banks are closed over the weekend, so there's no way that she can get the money to him by Sunday because the earliest they can process this transaction is on Monday. And she thinks, wow, this is a whole load of hogwash. She's like, this is ridiculous, right? Like, I can send all of the money in my account to my friend on Venmo as soon as I want to, but I can't get the money to my landlord that I need to have an apartment, and she gets very, very stressed. But fortunately, Alice is great. Alice was a computer science student, and so she thinks, all right, I can come up with a solution to this, right? Like, this is what my engineering degree was for. So she comes up with this fantastic idea of digital money. So she goes home, she takes $1 out of her wallet, a US dollar, and then she scans it. And she's like, great, now I have a digital representation of $1. And she thinks, all right, well, people want to know that I'm not going to go and spend my real Alice dollar. So then she takes $1 and she locks it in a box and she takes a picture of it. And she's like, all right, everything is good. I have, proof that I can't spend this real dollar. And I also now have a digital version of my dollar. I've just solved all of the world's financial problems. So then she goes and she says, hey, Bob, I'm a nice friend, so I'm going to send you this digital Alice dollar. And she sends him, the picture, the scan of the dollar that she took. And she's like, wow, this is great, the first digital transaction. Unfortunately, Bob is up to no good. Bob is also a little bit conniving, and he thinks, wow, this is great, I have a digital dollar. And he realizes that he can just take this dollar and copy it, right? So now he has $1 and $2, and he says, hey, Carol, I'm gonna send you $2, like, isn't this great? And Carol thinks, wow, she's getting $2, but really, Bob is just cheating. So this sort of sums up, we have a lot of motivation to create digital representations of money, but the real question is, right, like, how do we stop Bob? How do we stop people from just creating money out of thin air, especially when it's on the internet, or especially if it's digital? I'm sure all of you know how easy it is to copy something. So that's sort of the end goal. So Alice thinks, she's like, all right, there must be a way to stop this, right? Like, first of all, I shouldn't have been friends with Bob because clearly he's up to no good. But also, right, like, there must be some way to stop people from copying money. So the first idea that she comes up with is like, okay, all of these, US dollars have these numbers on them. They have serial numbers. So I can just keep track of, all of the dollar numbers. And then whenever somebody wants to send money, they can call me. If Carol gets $2 from Bob, she can call Alice and say, hey, Alice, have dollars 1 and 3 been spent before? And if they haven't, then Alice can say, nope, you're good to go, those dollars are good. If they have, she can say, Carol, Bob is up to no good, you should stop being friends with him. So this works fine, but it also involves a whole host of problems, right? Like, this means that Alice has to be, on speed dial for every transaction that anybody ever wants to do, and she also has to know how much money everybody is sending everybody else all the time, and Alice doesn't really want to know that. So then she thinks, all right, like, this whole central issuing authority probably isn't a great idea. What if we had people who are sort of on, like, neighborhood watch, where you have a bunch of people who are looking at a bunch of different transactions to make sure that there are no Bobs out there who are up to funny business? So this is Alice's stunning insight. She's like a modern day Satoshi. But before we get there, we're gonna need to go through some basics. So I'm gonna talk about cryptographic hash functions for a little bit. So what is a cryptographic hash function? It's just like a normal hash function, right? It'll take any size string as input, spit you out some fixed size output, which is very nice. There are some key security properties that make this really important and that sort of underlie all of what the blockchain is. The first is that they're collision resistant. This means that if I give you 2 different inputs, it's really hard to find something where 2 inputs give you the same output. And then the second property is that it's hiding. So if you know the output of a hash function, it's hard to find what I gave you that comes in. Oftentimes those seem like they're similar properties, but for example, a really easy collision resistant hash function would just be an identity function, right? You give me a square, I give you back a square. You give me a triangle, I give you back a triangle. But then it's really, really easy for you to figure out what the input was because it's exactly what I spit back. The third property is called puzzle friendliness, which is a little wonky, but basically it means that if you're given some output and you choose a random prefix, it's infeasible to find sort of the postfix that makes those two things combined generate the output that you want. And this property is what underlies the creation of new coins in Bitcoin, the process that we call Bitcoin mining, which I'll talk about a little bit later. So now we have our hash functions, and this is great. So what we can start to do is build some primitives from this. And the first is going to be a hash pointer, which is a lot like a data pointer, except for just make sure that whatever data you stored hasn't been changed. So you have some block of data, you take the hash of that, and then if somebody like Bob tries to go in and change whatever you stored, you can say, oh, no, that's not right. I actually have some proof that this is not exactly what I stored. And so with a hash pointer, you can start to build these linked lists where you have blocks of data that contain hash pointers with the previous block so that you can verify that there's this chain of truth and that there's some order of events and that order is preserved. So this means, right, if Bob tries to go in and change block number 2, you can say like, oh, actually, I know there was a failure right here at block number 2, which happened after block number 1, and you can verify truth there, which is really great. We can also build, binary trees or something called Merkle trees, which have a very similar structure using these hash pointers, but in a tree system. And what's nice about this is that you can have proofs of inclusion in log n space, right? So we can have all of these sets at the bottom, but we only need, a trail of log n hash pointers to figure out what's in the set. So hypothetically, if we were to store a set of, these unused dollars, it would actually be really short for Alice to prove to Carol that the dollar that Bob gave her is actually in the set of unspent dollars. So now, we have all of these primitives. We understand what a cryptographic hash function is. What is a blockchain? Unsurprisingly, a blockchain is a chain of blocks. So these are the same blocks that we saw earlier, right, with hash pointers pointing back. I'm sure a lot of you figured this out already. This is a big surprise to me. And these blocks contain transactions and these things called UTXOs, or unspent transaction outputs. So a transaction is something, right, like Alice paid Bob $5, and an unspent transaction output is like, okay, here are all of the dollars that are just sitting in people's wallets that haven't been spent yet. And we model transactions as inputs and outputs often. So here you can see that we have, some input. Alice inputs $30 and gives Bob 10 and Carol 20. And then Carol can then, in another transaction, take that and give $10 to Dave and $10 back to herself. And we store these unspent outputs in a Merkle tree so that it's really easy to prove that the dollar that you're trying to send to somebody hasn't already been spent. And so sort of in the chain database or in the chain code base, this is what our blocks look like. You have some block header, which has some nice metadata like the height of the block or sort of the order in your chain. The previous block ID, which is that hash pointer that goes back to the previous block so that you know that Bob hasn't been messing around, the timestamp, and then it has the transactions root, which stores all of the transactions, and then the assets root, which is actually the root of that Merkle tree so that you can prove what dollars are unspent. So this is what the blockchain is. Super exciting. And so for our whole blockchain representation, we have our initial block hash because you want to know, okay, where does the chain start? And then we have an idea of some state, which is mostly just the height, the block that you have in the snapshot, which contains a lot of the metadata, which is useful in referencing. And so our interface sort of looks like you can get a block, you can get the latest snapshot, you can save the block and persist it, and you can finalize it and save the snapshot. So this is sort of what's happening in the chain code base. So now, you have this idea of storing data, of these unspent outputs, but the question is, right, like, where does this money come from, right? When people are like making millions off of cryptocurrency, like, where is that money? Is it like fake money? Like, what is going on? I don't really know. But what I do know is that this is how blocks are created in the Bitcoin world. So if you harken back to the puzzle friendliness property that we talked about with hash functions, this is basically what Bitcoin mining is. They're all solving a puzzle, but it's not like when you were like sitting on your living room and you're trying to like solve a puzzle, because it's a lot harder and the stakes are a lot higher. So the puzzle that you have to solve is you have to basically create a valid block point or a valid hash pointer. You have to find some combination of the previous block, right, all of those transactions and unspent outputs, the pending transactions, so transactions that people want to be included in this current block, some award transaction, which is a nice thing to include because it's what gives you like free Bitcoins, and the nonce. And the nonce is just something that you start at 0 and then you just increment it until you get a hash that matches sort of the puzzle output. And usually what this looks like in the Bitcoin world is that it has to be smaller than a certain number or start with like 13 leading zeros, right? So, you know, you have all of these Bitcoin mining farms in like Inner Mongolia, and they are just like incrementing the nonce as fast as they can in order to generate some hash output that has like 13 or 20 or, you know, a million leading zeros. And of course, the puzzle friendliness property of the hash function is what makes this hard. And the difficulty of the hash problem is adjusted so that you overall generate about 1 block every 10 minutes. And so the difficulty, of course, is like how small you need the hash problem to be, because that reduces the size of like the space that you're trying to hit. In Chain, we do something very different. Chain is actually a private blockchain and it's a multi-asset platform. So what block creation or what asset creation looks like here is a lot more like when Alice took the dollar and she locked it up in a box and then she took a picture of it, right? What we want to do is take like real world assets like US dollars or Starbucks rewards points or whatever you want and put them on the blockchain. So we have this concept of something called an issuance program, which is basically you have some issuing authority that issues some digital assets and you trust them to not go and spend those real world assets somewhere else. So here, right, like in our assets, we have the issuance program, and you know, a really simple example of what an issuance program is that it just needs to be like signed by someone, right? Like it's signed by Starbucks that these reward points are now only on the blockchain, and you can't go buy like a million mocha frappuccinos with Bob's rewards points. So now we have, you know, we know how we store transactions, we know how we create them, but how do you get everyone to agree, right? Like in Alice's neighborhood watch like world, how can we make sure that Bob isn't just approving all of his own transactions, creating loads and loads of money for himself, and just getting rich in his own world? So the way that this happens in sort of the Bitcoin world is something called proof of work consensus. And this is a way to basically economically incentivize people to like not accept bad transactions. So the crux of how this works is that, you know, there are a host of nodes who are all trying to, you know, create transactions, mine new blocks, and approve transactions. And each of those nodes has their own chain, right? Their own idea of, you know, what all the blocks are. And the only chain that is accepted as valid is the one with the most work. Sort of like more colloquially, you can think of this as the longest chain, the one that has the most blocks, but really like how it works in implementation is that you take the difficulty of the problem for each of the blocks and you sum that up. And whichever one is the most difficult is the one that is accepted. So now if you're if you're a miner, you're really strongly incentivized to check for the transactions and make sure they're all valid. And if there are any invalid transactions, to reject them, because you want to be able to produce the block that is accepted as valid so that you can get your reward transaction. And if you think that everybody else is also discarding these bad transactions, then it makes it really unprofitable for you to accept them. So that's sort of how this works. And the idea is that, you know, there's such a large Bitcoin network that it's really hard to collude. You can't just like call up all your friends and be like, hey, like accept my transaction that gives me $1 billion, because you would spend all of your time calling people. So yeah, so here, you know, you have everybody with their different chains, and everybody wants to have the longest one or the one with the most work. So they're all incentivized to work together. In the chain world, this is a little bit different because we're a private blockchain. So what that means is it's an invite-only party, you know, so you can have like a little bit stronger assumptions about what everybody is up to. So we use something called federated consensus. And basically what that means is that all of the participants will send their transactions to some generator nodes. And these are like, they're not special in any way, except for they generate blocks. And then these blocks get broadcast to a network of signers. And you need like M of n signatures in order for a block to be accepted. So that could be something like 1 of 2, or like 5 of 7, or like 1 of 1,000,000. It's whatever you want. And the reason that this works in the chain world, right, is that you aren't suspicious of there being Bobs out there. Like, for example, this could just be all of the Starbucks stores. And you don't, like, no Starbucks store really has a strong incentive to create a bunch of fake rewards points. So you can assume that they're all pretty much okay. And what you want to control for is actually like failure or some sort of like lack of availability. So here, you know, you have some generator and some other signers. And if you get the right number of signatures, then a block is accepted as valid by all of the other participants in the network. So for us, sort of how we like validate and signing blocks. So if you're a signer, you're gonna wait and we broadcast new blocks on a channel so that you know like what the latest block height is. Then you'll go ahead and check to make sure that you can get it, verify the consensus program, which makes sure that, right, like the block that you got actually matches up with the block that came before it, that everything is good there. And then we validate it, and then you sign it and you return your signature. So this is sort of how, in the chain world, a signer would get a block and validate and sign it. If you're curious about sort of how the rest of the ecosystem works, the whole system is open source. So you can, right now, or when you go home, go onto the chain GitHub, run your own blockchain on your machine, issue yourself a ton of fake digital assets, send them to your friends, do whatever you want. It's you know, my #1 hobby. So now your question might be like, oh, right, now like I'm a blockchain expert. Like where is all of this ICO money that I've been promised, right? Like how can I get my like $300 million check in the mail? And unfortunately, I have no idea how you do that. If I did, I would not be here speaking to you all. But I can talk a little bit about Ethereum, which is, you know, the magic money generator these days. And so in Ethereum, you have a slightly different model from these unspent transaction outputs. You have something called accounts. And so accounts have a nonce, which makes sure that transactions don't get, that don't happen multiple times. Accounts have some balance, right, which is just like your bank balance. They can have contract code, which is like the secret sauce of Ethereum, right? Like these are the smart contracts. These are compiled bytecode that basically that accounts can run on a certain address. And then they have some storage, like they can store some data. And basically what happens in an Ethereum world is you can send transactions that contain these messages that send value and data between accounts. So let's say I can have my own account, right, that stores my personal balance, but I can also create a contract that just exists in the ether that has some code that will run whenever I send, you know, the right message. If I send like my secret password or send like my not so secret password, it'll run that code and can also send value to other accounts and to other contracts. And the other, you know, piece of this is that when you validate blocks, you also validate the contract execution. So each node in the Ethereum world doesn't just store all of these unspent outputs. It actually stores the accounts and the states that are involved there. And you have this notion of like state transition. So here, right, you have all of these accounts with different balances, and you have some transaction which contains some other data like 2 and Charlie. And then this actually changes the state of all of these nodes. You have a different set of accounts with different, you know, data in them. And that's what happens, and that's sort of what the idea of a smart contract is that it's this compiled bytecode that will run when you send a message to an account. And that these changes are sort of propagated throughout the network as everybody on the Ethereum network is confirming these blocks and validating them. So what this means, right, is that Alice can now send Bob if and only if her favorite character stays on the next episode of Bachelor in Paradise, right? And so like before, she would have to like wait until this happened and then go on and then send him money, and he could be like, oh, I don't know if he'll send me this money. But now they can both sit down together. She can write this contract and be like, see, you know exactly what's gonna happen once we get the message from ABC News on the Ethereum network, and then you'll get your money. So this is great. There's a lot that we didn't cover. I'm sure you're still wondering how to get your millions of dollars. I still, unfortunately, do not know. We didn't go over any proofs, so you're just gonna have to trust me that this is how all of this works and that it's all secure. There are some fun blockchain attack models, both from like the mining side in terms of like, if you're really, really determined to try and double spend, like how do you do that? There's been some drama recently around like hard and soft forks and different governance models. That's all very interesting, the economic implications. But for all of this, you can go on the internet. The answers there are sometimes unsatisfying, but there are a bunch of great meetups around. So hopefully this is a good overview of some basics of blockchain, and then I can take any other questions.
Any questions? Walk on up to the mic. It's right by you.
So you explained a bit about proof of work. I was just wondering if you knew about the new model that they're moving towards, proof of stake.
Yeah, a little bit. I probably can't explain that well, so I won't try. But there are like some interesting new models like proof of stake, which like doesn't involve doing like computational work, but has something to do with like staking money. And then I think I heard about like proof of time. I actually don't know how that works, but they had like a nice website with a lot of animations. So if you want to check that out, it'll probably be really interesting.
And then how would the transaction know about the bachelor on ABC. How would you go about that?
Yeah, sure. So there's some conversation about like oracles on the Ethereum network, which are basically ways to get information about the outside world. And so an oracle in this sense might be, right, like one way to do is ABC News might, like, if they're incentivized, right, they can create a contract that like has some state which says like, you know, which lists all of the people who are still on Bachelor in Paradise. And then you can go in and be like, oh, who's there? And then if the person that you want is there, then you can go ahead and send the money. And if not, then you don't have to. And there's some conversation right now about how oracles can be built in a decentralized way, right? So that you don't have to rely on ABC going in and uploading their contract or creating their contract. But to my understanding, that's sort of an open question. So if you come up with a great solution to that, that's probably a good way to get millions of dollars.
Any other questions? All right, thank you so much, Vicki.
Thank you.